Now I'll show you how they do it. And what is the plan? The plan is, okay, they've got the EPR pair. Alice is 1 kilometer away from Bob. Alice is holding on to A. Bob is holding on to B. And Alice is going to be shown red or yellow. And she's going to do rotate by some angle operation on her qubit A. And the angle she does is going to depend on whether she saw red or she saw yellow. Okay, similarly, Bob, 1 kilometer away, is going to be holding on to B. He's going to see either orange or green. And he's also going to do like rotation by some angle beta on his qubit. And the amount he rotates by is going to depend on whether he saw orange or green. Okay? And then you can think of it, okay, this is all happening in like a nanosecond or something, but like you can think about it as, well, Alice did some rotation, Bob did some rotation, and it's erased from this board, but like that will, like Alice will move this pointer like some amount, and Bob will remove it some other amount. And so the difference of the two amounts will be what the final resulting state is. And then they are going to both measure, but they're privately going to measure their own qubits or extract their own qubits. And they're just going to say back to the referee whatever the measurement outcome was. So in that way, there are, Alice is saying some bit A and Bob is saying some bit B. And we're going to analyze it as though they'd like measured did extract all, and they did it at the same time. And that might make you feel a little bit uncomfortable at first because you're like, oh, but they're far apart. Like, can you do this? But remember, like in the last few lectures, we really took care to make the point that if you have operations on separate qubits, even if they're unitaries, even if they're measurements, it doesn't matter the order you do them. You can do them these ones first, then these ones. You can do them in the opposite order. You can do them simultaneously. You'll get the same mathematical results no matter what. So we're just going to see what the new state is after Alice does her rotation, after Bob does his rotation, and then we're going to apply this chart to see what the bit outcomes will be when they both measure, and then we'll just calculate. Okay, so let's see, where shall I write it? Let me write up here, actually. Okay, so now I'm kind of defining Alice's strategy. Alice's strategy really is now like if she sees red, she's going to do rotation by some angle, and if she sees yellow, she'll do rotation by some other angle. So in some sense, her strategy is actually like labeling red and yellow by angles, rather than labeling them by bits. So let me just write it. If Alice sees the strat, red, she applies, let's say rotation by alpha r. Just this whole alpha r is some angle on A. And she'll decide what that angle is in a moment. And if she sees yellow, she'll apply rotation by alpha y on A. In addition, if Bob sees orange, he applies rotation by beta O on B. And if he sees green, he'll do rotation by some angle beta green on B. Okay, so as I said, it's really like Alice picks some angle here, I don't know, alpha r, between 0 and, well, it can be anything, but it'll be between 0 and 90 degrees. She picks some angle here, alpha y. Bob picks some angle here, beta O, and some beta G here. Now, okay. So what happens? Let's say, so after they do this, the joint state goes from, let's start out at EPR pair, which is EPR 0. It goes to EPR theta for some theta. And let's do an example. Let's say the coins were red-orange. Okay. Then, well, you tell me, what will theta be in this case? Yeah. So in this case, theta will be the red angle minus the orange angle. Because, well, it's off the board now, but we saw that, like, okay, Alice's rotates by the red angle in this case, so theta gets the red angle added to it. Bob does rotation by beta orange, so the angle gets beta of orange subtracted from it. And the angle started out at 0, so the new angle is the red angle minus the orange angle. Now, in this case, what is the... well, in this case, Alice and Bob are actually hoping that A equals B, that Alice's measurement outcome equals Bob's measurement outcome, because that's the win condition when it's red-orange. They're hoping that A equals B. So the probability that A equals B, we have it right here in my scratchy handwriting. It's cos theta squared. So therefore, they hope that theta is close as possible to what number? Zero, yeah. Because they want this to be 1, and it's cosine of 0, which is 1. Okay? So in their ideal situation, the state remains EPR 0 after their 2 rotations, because then that's the situation where they always, for sure, have the same measurement outcome. So they're hoping that theta is 0 in this case, i.e. they want this to be 0. So they want that the red angle is approximately as close as possible to the orange angle. Sorry that I'm writing all these colors in blue, but I want to keep switching markers. Okay, so that's in the red-orange case. So 1 out of 4 times, they're going to see red-orange, and then how well they do is basically dictated by how close this red angle is to this orange angle, which is interesting. It's like saying, oh, they really want this angle to be very close to this angle. So let's just think about the other 4 cases, and maybe you can kind of guess what's going to happen. So similarly, if it's yellow-orange, then theta becomes whatever the yellow angle is minus the orange angle. It's always like this. And then they win if and only if, again, A equals B, because in the yellow-orange case, they're trying to be the same, which has probability cos theta squared again, which again means they want theta to be as close to 0 as possible, which means that they want this as possible. So they want alpha yellow to approximately equal beta orange. Okay, and similarly, I mean, for yellow-green, they want the yellow angle to be approximately the green angle. And the last one is a bit different, but it's not so crazy or anything. If it comes up red-green, again, theta is the red angle minus the green angle. And they win now if A differs from B. And the probability of that is the probability that they get different things, in my terrible writing, is sine theta squared. So they really want this to be close to 1. So what angle theta has sine theta squared equal to 1? It's 90 degrees. So they really want the difference between the red angle and the green angle to be 90 degrees. In other words, they're like hoping that the red angle is like approximately perpendicular to the green angle. Does that make sense? So these boxed things are like what they're really kind of hoping for with their strategy. Remember, their strategy is defined by how they choose these 4 angles, which they can plan on in advance. And as I said, it's really like they're going to come up with some angle for red, some angle for orange, angle for yellow, angle for green. And they know that like with probably 1/4 each, they're going to face this situation, this situation, this situation, or this situation. This situation makes them want to have the red angle be very similar to the orange angle. So if that was the only thing in the world, they'd make this angle equal to this angle. In the next situation, they want this angle to be equal to this angle, ideally, or as close as possible. They want this angle to be equal to this angle, but they want this angle to be like as opposite as possible, meaning perpendicular from this angle. And that's a tension, right? Like you cannot have angles such that these are like the same 90 degrees from each other. And it's the same tension, which is the reason that when they were classical and they were labeling by bits, they could only win with probably 3/4, because there's just no way to have 4 bits that are like equal, 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 not equal. But angles are smoother, right? Like you can, there's more options at play. It's more flexible. Like you can kind of have, it's more possible for one angle to be sort of close to another angle. That doesn't happen with bits, right? They're either equal or not. So actually, I'll let you think about it. I mean, the point is that like in the bit case, they kind of have to be right with probably 3/4 and wrong with probably 1/4. And there's no way they can spread it out. They have to like pick one edge and have all their wrongness on that edge. But here they can spread out it's still true that they can't be perfect, but they can spread out their sort of 1/4 wrongness evenly over all the edges. So, yeah, finally I'm going to ask, I mean, can you suggest some angles for Alice and Bob to use? Yeah? Oh, 0, 30, 60, 90. Great, let's try that. So, I can depict an angle just like, I don't know, like on a clock. So like I will depict, I don't know if this is like 30 degrees, I'll just draw it like this. So the suggestion was like this is 0, 30, 60, and 90. So actually let's calculate the probability of that winning. Okay, so the win probability of this strategy, 0, 30, 60, 90. Okay, so there's 1 in 4 chance that they do red-orange. So it's 1 in 4 times something. And then the chance that they win is cos of the angle difference between red and orange, which is 30 degrees squared. So what is cos of 30 degrees? Is it cos 30 degrees squared is 3/4? Can somebody confirm that? Thank you. So it's cos 30 degrees squared, which is 1/4 times 3/4. Plus, there's a 1/4 chance that it's orange-yellow. And there, again, their winning probability is cos squared of the angle difference. And the difference between 30 and 60 is 30. So we get another cos 30 degrees squared, which is another 1/4 times 3/4. And there's a 1/4 chance that it's yellow-green. So there, the angle difference is again 30. So it's like times cos 30 degrees squared. So that's another 1/4 times 3/4. And then there's a 1/4 chance that it's red-green. And actually here it's perfect, because now we had 0 degrees and 90 degrees. They're perfectly perpendicular. So sine of 90 degrees is 1. So this is times 1. So if we add these all up, we get 3/16, 3/16, 3/16, 4/16. That's 13/16. And actually, one thing is, you can already tell it's beating 3/4, Because like even up to here, you were like on track for getting exactly 3/4, and then you're like, haha, like I got better. So this should be bigger than 3/4. Can somebody tell me how much this is? Let's see if I can do it. It's 75% plus a 16th. The 16th is like what, 0.06 or something? So it should be like 81%, is that right? Cool, 81%. So that's great. With this strategy, they can win with probably 81%. And that's also good enough. I mean, you can now like do this experiment like 1,000 times, and they should get it right 810 times. Yeah, so that's good. Now actually there's a better strategy, a little bit better. Can somebody think of a little improvement on this? Yeah? Yeah, good. I think that's going to be it. So the suggestion was, here they kind of went up in thirds. And one feature was that like, you were like doing like pretty good on this edge, pretty good on this edge, pretty good on this edge, and perfect on this edge. You might guess that somehow by symmetry, the ideal situation is to be doing equally well or badly on all the edges. That would maybe be at least something to try. And the suggestion was, yeah, let's do 22.5 degrees. In other words, let me draw it over here. Okay, this is the perfect opportunity to use these pens. Let's try it like this. Do 0, and then 1/4 of 90 degrees, and then 1/2 of 90 degrees. I don't know if you can really see this. And then like 3/4 of 90 degrees, and nothing at 90 degrees. So we kind of divided up the 90 degrees into quarters. And then we'll see how that does. Yeah, so I guess the point is like these two have an angle difference of 22.5, like 1/4 of a right angle. These two have a difference of 22.5. These two have a difference of 22.5. And these two have a difference of 22.5 away from the ideal. They're like 22.5 away from being at 90 degrees. So with this strategy, we get cos 22.5 degrees, which, by the way, I happen to know is somewhere around 85%. And this one is going to be cos 22.5 degrees. It's also 85%. This one is cos 22.5 degrees. 85%. Wait a minute, this was wrong. Hold on. Oh, this is like sine 67.5 degrees, which is also known as cos 22.5 degrees. That's the nature of sine and cos. So this is also, yeah, 85%. Yeah, so this averages out. So here you've got set it up so that you do equally well in all four of the cases, and that equally well is cosine 22.5 degrees, which I think is like 1/2 plus 1/2 root 2 for some reasons, but anyway, it's like about 85%. And that's, you can prove is the optimal strategy. We don't have to prove that it's an optimal strategy. You can, we won't, but like, it's actually kind of intuitive maybe that it is. But anyway, it shows you can win using an EPR pair with probably at least 85%. And so again, like it somehow, I don't know, it used the fact that, I don't know, you didn't have to assign like these hard bits 0 and 1 to each one of these four positions. You could assign like angles which allow you to like interpolate smoothly between the possibilities. Yeah, so the CHSH game came out in 1969 after Bell's more complicated version that was hard to understand came out in 1965. It's funny, you'll see in like quantum computing literature this famous phrase, Bell's inequality. Bell's inequality is his proof that classical players could not win the game with more than this probability. So in the CHSH setting, Bell's inequality, this famous inequality, is literally saying, oh, if you're classical, you can't win this specific game with probability better than 3/4. Which is a pretty simple thing to be called Bell's inequality, but it is. But then CHSH came out with the simpler game, which is more easy to comprehend, and people pretty soon tried to like actually do the experiment with like a couple of photons or electrons or whatever. This was like in the 70s. And by 1972, Clauser, which is this C, he did this experiment with Friedman. And in his experiments, he got win rates for the players, which I guess were some kind of physical apparatus, that was like bigger than 75%. So it kind of demonstrated it, but it wasn't like the most compelling demonstration, partly because, well, the win rate wasn't maybe that high compared to 75%. Also, the apparatus was not physically separated far enough. So like it really should be that like if you separate the apparatus like this far, you should demand a response rate that's like faster than the speed of light going between these 2 points. Because otherwise it's like there's a loophole. Like maybe somehow they are, even though you didn't design them to communicate with each other, maybe somehow something in nature is making them communicate. And he didn't do that. They were like, I don't know, on a table, and he couldn't get them to respond fast enough. But, you know, it was still pretty good. And then this guy called Alain Aspect. I should mention though, but Clauser won the physics Nobel Prize in 2022 for this, and Aspect also won the Nobel Prize in 2022 for doing the experiment like well. So Aspect and some other collaborators, Dalibard and Roger, in 1982 really managed to do this experiment well. It was also like on a table where I think it was literally separated by about like 1 meter, but like he really got the response times very appropriately fast. And the win probability that he was demonstrating was like 84%. So people are like, I think he really did it. Maybe the only like loophole was how did he implement the referees? So the referees have to be random. And okay, how do you get randomness in real life? It's a little bit hard to say. But like he had some very like, I don't know, plain pseudo-random thing where like it had some electrical pulses and just whatever the pulse was, he used that as his source of randomness. So people were like, well, maybe it's like pseudo-random, but I mean, basically it was fine. So yeah, he won the Nobel Prize for that. The third Nobel Prize winner was, Holt? Or was it Horner? It was one of the H's. No, sorry, it was Zeilenberg, who's not mentioned here. But Zeilenberg actually was the person that co-invented teleportation that we saw last time, and also studied entanglement. So it's pretty cool that like the last Nobel Prize in physics, or the 2022 one, is all for stuff that we studied in this lecture and the last lecture. And I can mention that like the ultimate version of this experiment, or the most recent ultimate version of this experiment, was done, I think in like 2017 on like the campus of University of Delft in Amsterdam. And they really did it with like the 2 qubits in different buildings on campus. Like they were like 1 kilometer or so apart. And they had to get their like fiber optic cable to move the EPR pairs like far apart and put them in fridges, and then they did the experiment. And it was really properly done. So yeah, you can do this experiment, you can verify quantum mechanics and prove EPR wrong. Okay, so we'll stop there. I have office hours today, so I might see you then. Otherwise, I will see you here Monday. There is a test, of course, on Monday, here at 7 p.m. And then, believe it or not, we're going to have class on Tuesday. But that's when we're going to start factoring, so it'll be good.